Hi everyone and welcome back to Digital Design with Verilog course. So in this lecture, like in the previous lecture, we have covered about half adders. We learned how to code a half adders. I have shown you live coding demo for Verilog code, and we learned a few things about Verilog code as well. Okay, we compiled the code, we ran a test bench, and then we have seen the results as well. Okay, so in today's lecture, I will first of all solve the assignment problem, that is implementation of full adder with different levels of abstraction. Then we learn bit about Verilog value set. What is value set? There are different types of values in Verilog. We learn about those, that is known as value set. Then we learn about numbers in Verilog. What kind of numbers is defined in Verilog? Keywords and tokens. Okay, keywords. Inside this keywords we learn about assign keyword. Okay, until now I have been using assign keyword, but I have not explained to you what is assign keyword. So in today's lecture we'll learn about assign keyword. So in the previous lecture, actually I told the expression for carry logic, right, wrong, that it was a mistake by on my behalf. The carry logic will be AB into C in A's or B. I told A into C in A and C in, or B and C in. That was wrong on my behalf. It will be this A, B, that is A and B, or C in and A's or B. Okay, that was a mistake on my behalf. So I hope you have rectified, because you have studied digital obviously and you remember. So the data flow level modeling, right, will be exactly similar to a half adder. Whatever I have taught you, it will be exactly similar. Here there are two boolean expressions, s equals to a's or b's or c in. Exactly that is what is happening. S equals to a's or b's or c in. Just a assign statement is there. Don't worry, today we'll learn about assign statement. Then we have c out, that is equals to a and b, or c in and A's or B. Okay, that is the expression for C out. So two Boolean expressions, two assign statements in data flow level of modeling. Now again, full adder implementation, same thing only, nothing will change. Here I have again just what has changed. There is a always block, end block, and this is similar. So you might have a doubt, sir, then what is the point? What is the point of writing behavioral code and data flow code if they are both same? They are same for a very simple example. Once we'll go to the complex example, you will see few things you will not be able to do with data flow level of modeling. You have to stick to behavioral level. We'll come to those complex example. We have just started, so obviously things will be a bit similar, but once we reach the complex level, you will see how much different they are. So like this will be same only, the expressions are same, so this will be almost similar. Now the interesting fact, if I come to the gate level modeling. So if I come to the gate level modeling, I see like I have two XOR gates, right? This is one of the XOR gate, this is the other XOR gate. So this is A XOR B. So this is A XOR B, S1 is A XOR B. Okay, this is the first XOR gate. Then what I do with the second XOR gate, like the result is S1, let's say, and this is the intermediate result. This is the intermediate result. So S1 XOR C in I do in the next step. Ultimately that is my S, that is what I store. So S1 is just a intermediate value because I have to connect. So I hope you understand the interconnections also. I am telling it here, right? The interconnections are automatically happening, the wiring inside everything is happening automatically, but here I am telling the interconnections. So I hope you understand the difference as well from here. Okay, so some logic is done. Let's do the carry logic. I have, okay, this is written wrong. This will be C in and, or like I can write in brackets, A XOR B. Okay, so this A XOR B, right, I already have this value in S1. So I will do, first I will do A and B, that is already done. I will store it in an intermediate wire, that is C1. Okay, C1 is stored. Now I am taking another AND gate that is doing what? That is doing that whose output is C2, like another intermediate result C2, and that is ANDing what? S1 and C1. So S1 is this, okay, S1 is this, and C1 is this. I am doing the AND of these two. So and then I'm showing the result in C2. Okay, then there is another OR gate, that is U5, because I have to ultimately OR these two results. So this is C1 and this is C2. So ultimately if I OR these two, I will get my carry. So this is what my C out equals to. Okay, so pretty straightforward, nothing that much out of the blue. So in the transistor level, what we'll do, gate level I have modeled. So this gate, right, I will make my own gates. That is the difference. I will make my own gate. So XOR gate is my own coding, own transistor OR gate. So let's understand the OR gate, because I have not explained to you the OR gates. So in the OR gate, like I will name these nodes N and P. Now same thing only here. the inverter is here. I don't need any specific inverter for A and B. So let me solve the pull-up network first. Okay, so I have a two PMOS. This first PMOS has, like, let's remember the sequence is drain, source, gate. Okay, so in this first top PMOS, right, the drain is connected to P and the source is VDD. So source is here VDD and drain is connected to P and the gate is A. Okay, for the second PMOS, the gate is B, the source is P and the drain is N. Okay, solve. Let's solve the below network NMOS. So in this NMOS, right, both have common connection for the drain. So both have drain connected to N, both have common connection to VSS. Okay, and both have gate as A and B respectively. Okay, so this is about the NMOS network. Now let's solve for the inverter, because ultimately I have to invert it to get my A or B. So I have an inverter as well. So this is what it does. It does, like, it has N as its input in the gate, right? Both the inverter has N as N as its input to the gate. Then I have VDD, VSS. So VDD is the source for this PMOS and C is the output, right? C is the like OR output. So C is the output for this OR gate, that is here, and for this PMOS and NMOS both are common. Okay, and for this NMOS the VSS is the source, that's why VSS is here. So pretty simple, pretty straightforward. Okay, so before obviously coming to the next topic, I will quickly move on to the code and I will explain you the code. So let me show you the code quickly to you guys. Okay, so yeah, I think you guys, where is the code? Yeah, okay, some reason it is not coming out, just hold on. Yeah, now I think you will, yeah, now I think you will be able to see the code. Okay, so yeah, this is the code basically. I hope you are able to see. So now I will come to the half adder we have already done. So the test bench for full adder is already written. So in full adder, right, just the, like, everything will be almost similar, but the test cases will increase. Why the test cases will increase? Because now I have 3 inputs. Previously in the full half adder I had 2 inputs. As I have 3 inputs, so the test cases will be what? 2 raised to power 3, that is 8 test cases. So I have 8 test cases, so I am testing for all of the cases. Like the code is almost similar. So let me again rerun the code here. So I will go back to my full adder implementation with Dataflow. Like, Dataflow is nothing, just I have to run the code, that's it, nothing new. So Dataflow, I will just quickly run the code for the Dataflow level. Okay, so let me run the code. I Verilog, then do VBP. So if I run the code, if you can see, like, whatever desired output you wanted, you are getting the desired output. Same for the behavioral. I will not like compile for the behavioral, nothing will change, just the code implementation inside the module will change, right? Outputs will not change, this is same. Okay, gate level, I will compile, because few, like, the code inside has changed, like, and you can check whether you will get the right answer or not. So like the test bench will be almost similar, there will not be much difference. So now again if I compile this, okay, you are getting the same output, but somehow, right, if I change something, let's say I messed up here, this is, let's say, C out and this is my S. Okay, so then things will be messed up. If we see, okay, this GTK got opened, sorry. Yeah, if you see, okay, again I'm sorry, this one, yeah. So now if you see, right, for this you are getting the weird output, this should not be 0, right? This is my S, this should not be 0. Okay, so like that you cannot mess up. But if I do something else, right, if I do dot C out, I will explain this method later on, don't worry, this is, it's separate topic. Dot C out, then do it this in brackets. Okay, but if I do dot C out, right, then I have to implement the same procedure for everything. Then if I do dot S, then implement the bracket. What Verilog understands, I will explain just in a second, just hold on, give me a bit of like time to write this. And this is dot B and this is dot C in. Don't worry, this is in like separate topic, I will teach you this one, but I'm still explaining you now. So now if I do this, right, now my code will not be messed up. If I again, okay, why is this GTK opening up? Yeah, this one and then this one. Okay, so now if I see, right, I'm getting the correct output. You see here I was getting the wrong output. Now I'm getting the correct output, even though I have messed up in the sequence. Why? Because Verilog understands if I do dot C out, right, it matches with the module input port. So in the module input port, there is a port named input port named sorry, not input, sorry, output port named cout. So it will exactly put this variable inside this cout. Okay, so nothing will be messed up here. So that is the advantage of these type of representation. Okay, I hope you understand this dot cout. I will explain this later on as well. This will come, don't worry about this. So like this is another advantage of these type of implementation. When you have multiple inputs and outputs, right, it's better to like give input like this, else you will mess up, somewhere you will mess up. Okay, so again, if I do the transistor level, like obviously nothing will change, everything will be same only. So if I implement the transistor level, so like I have to like uncomment all the gates. Okay, XOR gate, OR gate. XOR gate was previously made, AND gate was also previously made, just OR gate has been newly made. Okay, so now if I again compile the code, like there is nothing much to see in the outputs because outputs will be same only, it's a full adder. So whatever you expect, you will get same output. Okay, whatever the expectation is, you will get the same output. This is 0 1. Okay, something is messed up. This should not be, this should be 1. Okay, something is messed up here. Oh no, this is 0 0 1. Okay, this is fine. Yeah, this is 1, this is 1 1. Yeah, this is fine. Nothing is messed up. Okay, I was just thinking something else. Yeah, 1 1, this should be 0 and carrying, yeah, 1. Yeah, everything is fine. All the outputs, whatever you want, you are getting the same output. Okay, so yeah, I hope you understood the code. That was about the coding part. Now I will quickly move on to the like the next topics basically. So next topic is this, right, the value set. Okay, so value set is in Verilog, right, there are mainly 4 types of values. Okay, this is also like a what can I say, this is also like a data type. There are other types of data type, but this is also one of a data type. Okay, so in Verilog we have 4 types of values. One is 0, another one is 1, then we have x and z. So 0 basically means logic 0, 1 basically means logic 1. This is what we study in digital circuits. Okay, so these are familiar to you. False condition, or in hardware circuits, right, sometimes they are taken as logic levels, or they are taken as condition in the hardware circuits. Sometimes we define it as false condition. 0 is known as a false condition and 1 is known as a true condition. Okay, so this is basically the hardware. Now let's come to x and z. So x is basically unknown. Unknown means I don't know. That is what unknown means. It is undefined or unknown logic. I don't know what it is. What is x? And z is high impedance state. High impedance means if a wire is there, I have defined a wire and I have not connected it with anything. I have kept it floating. So that is what z means. Z means it is in floating state or in unconnected or tri-state region. Okay, so or high impedance. So in both cases, x and z are undesired values. If in one of your outputs, right, let's say I will just go back to the code again. I will show you the code. So here somewhere you got z. Okay, you got z. That means you have messed up somewhere. So somewhere you have got z in here. That means you have simply messed up. Okay, you have done something wrong. So you don't want to do that. So just be careful about that. Just checking one thing, if this comes or not. This actually, okay, this doesn't come. I was thinking that a visual should come. This is not coming. Okay, in the screen recording, that is fine. Okay, so yeah, that is what I was trying to explain. Just hold on a second, I will check once more if it does not come. Sorry for that. So yeah, again I will go back to my writing pad. So let me go back to writing pad. So yeah, so these are undesired values. That means we have made some mistakes. We have made some mistake on our code. We have to go back to our code, some logical or compilation mistake, like syntax error or some error we have made. So we have to be careful regarding that. Okay, some mistake. So x and z, I will explain more about x and z, don't worry. Like today's video will be about this only. So first thing is, if I do z and 0, right, the result will always be 0. Okay, if I do z and 1, the result will be unknown, because one thing I know, if I do AND operation, anything I have with 0, the output will be 0. I don't care about the other things. That's why this is fine, this is defined. But if I do AND operation with 1, I don't know, right? Z is also a unknown value to me. Now I know AND with 1, right? It does not, like, this 1 is not the deciding factor actually. Why? Because if I do 0 and 1, I will get 0. If I do 1 and 1, I will get 1. So which decides the result? The result is decided by the left hand side, not on by this one. So that's why the result of Z and 1 is unknown, because I don't know. It depends on this value, right? I don't know. That's why it is unknown. Then Z or 0 again is unknown, because you do OR with any value, 1 or 0 or 0 or 0. It can be 1 or 0. So it is again decided. It is again decided by the left hand side. That's why it is unknown. And if I do Z or 1, this will be 1, because this decides, right? Whenever I have 1 and I am doing OR, it will be 1 no matter what is on the left hand side. That's why. Okay. So this is about this one. So Z XOR 0 is again X, and Z XOR 1 is also X, because these are all undefined. This cannot be defined. Okay. Now let's say I have a wire A. Okay, in Verilog, right, it is very tricky. Wire A value is 0. Okay, if it is value 0, it can be many things. In real life, I know what is 0. In real life, 0 is 0. In real life, it is just a number. 0 is a number. In Verilog, there can be many things about this 0. This 0 can be a logic 0, okay, in a digital circuit. This 0 can be a strong 0 for grounding or pulling down, okay, strong 0. Okay, so basically like a ground pull down network. Okay, this 0 can be a false, like conditional false statement. This 0 can also define as a low state. Okay, like what do I mean by low state? Like sometimes it is not ground, right? You have digital levels. Sometimes your digital levels can be, the higher level can be plus 5 volt, lower level can be 0 volt. Then in this particular circuit, it is 0 volts, 0. But for another type of circuit, let's say I have another type of circuit which has logic high as 3 volts and logic low as 1 volt. So in that case, 0 will be defined as 1 volt. Okay, so like that also you can say. Or your low level is minus 3 volts, then your low state will be minus 3 volts. Like that you can define. Okay, again the same thing, exact same thing I will copy for 1 as well. Okay, exact same thing I will copy for 1 as well. So if I just change everything here, okay, so if I change this to 1, it is again, in real life it is just a number, but in Verilog it can be logic 1, it can be a strong 1. Okay, strong 1 means supply, VDD. Okay, VDD, it is connected to a strong 1, that is supply. Or it can be a true conditional statement or true case. Okay, this is case, this is also case. Like a logical statement output is true, that means it is 1. Okay, or it is high state, not low state, it is high state. So high state in this case will be 5 volts, or in this case it will be 3 volts. So there can be many things in Verilog. Okay, so let's now understand this unknown value a bit more. Okay, so let's say you have a circuit, and you don't know, this is a AND gate, and you don't know the one of the inputs of this AND gate. You know the other input. Or sometimes what happens is, like in this particular case, right, can you tell me, pause the video, can you tell me what will be the output Y? Okay, if it is 1, and if it is, this is just AND gate, if it is 0. Okay, very simply, for this case the output will be unknown. That's why Verilog has to have a state unknown, because I don't know what is the output. Okay, and I will say when will this question mark come. I will say about that just in a second. And for the second case, my y will be simply 0, because 0 and with anything will be 0. Okay, so the second case is very easy. The first case is a bit difficult. Okay, so this one is done. Now when will these kind of states come, or unknown kind of case will come? Okay, so x is basically unknown, as mentioned previously, unknown. So what I can say is that I have this wire, right? I have this wire. So I have this wire. Now let's say two wires are connecting to this wire. Okay, this is a wire A, and I have a wire C, and I have a wire B. Wire B is a strong one. What is strong one? I will tell later on. Let's for now just understand it is VDD, and wire C is a strong 0. Don't worry about the strong keyword. Just understand it is 0. It is 1. Okay. So they are happening at the same time. Okay, they are trying to write, this C is trying to pull down to 0, this B is trying to pull it up to VDD. If something like this happens, that means my wire A will have an unknown state. Wire A will have an unknown state. Okay, so this, right, is actually not synthesizable. Of course your wire will have some value. It will take, like in real life, if you connect 0 and 1, right, something you will get something at your output of the wire. Something will happen, something will burn, blast, something will happen. But this x, right, this x is only for simulation. In real life you will see something will blast, something will happen, short circuit has happened, it will catch fire or something. So this x, right, is only for simulation, not a real life number or something. Okay, in reality you will not ever see this. So Verilog has to say something that, hey man, I am not able to resolve this conflict. There is some conflict here, right? There is some conflict. Verilog will say, hey man, I am not able to resolve the conflict. Please, you have to fix it. Okay, but this x is only for simulation purpose. This is not a real life number or value. Okay, you will never see a real life number or value. There will be, basically what will there be? There will be metastability, and after a certain point it will latch onto some value, either 0 or 1. Okay, either 0 or 1, it will latch onto some value. There will be metastability. I will not go too much in depth of metastability, but there will be metastability, and after a certain point of time it will either latch onto 0 or 1. Okay, metastability between 1 and 0, and after a certain time it will latch onto some value. Okay, so yeah, that is what I wanted to discuss, right? That is what I wanted to discuss. Same as a D flip-flop. If you have a D flip-flop, you know you are giving it some input, some clock, right? So the initial value that we give, right, we cannot instantly take output from this. There is some delta t or propagation delay for the Q to store the values. So it's similar to that only. Okay, so initially when I have made this D flip-flop and I'm just giving it the input at 0 nanosecond, and I'm taking some output at 0 nanosecond from this D flip-flop, will I get some value? It will be unknown, right? Because this is not a valid value. Whatever I will get, this is not a valid value. This will be some garbage value that I don't want. After storing some D value, it will take some delta t amount of time to store that value, right, in the D flip-flop. Okay, so this is about the Q. Very important point that I wanted to say, that x is basically unknown. It is not synthesizable. X is, I will say here, x, right, the value x is not synthesizable. Not synthesizable meaning we cannot synthesize in real life, or we cannot see it in real life. Okay, not synthesizable. So that is the case. Another example, if the D flip-flop or any variable that is uninitialized, then also it takes up the value of x. Okay, so I hope you have understood the x concept. In real life, x doesn't exist. X is basically, we don't know what the value is, 0 or 1 in simulation. Okay, so now let's come to the high impedance state. So I hope you have seen a tri-state buffer. If this enable is 1, then whatever the input signal I have, it will just simply pass it to the output. If enable is 0, this y, right, will be floating. So that's why when this, like when this enable is 1, then okay, just hold on. When the enable is 1, then my output y is equals to a. When my enable is 0, then my output y is equals to high impedance state. I have to define this state, right? It is simply floating. In Verilog, how will I define high impedance state? By z. We define high impedance state by z. Okay, z is high impedance, but this, right, is occurs in real life. High impedance actually occurs in real life. So this is properly synthesizable, occurs in real life. Although both have unknown values, but z, right, is a absolutely synthesizable number. It is high impedance. Basically, it will be a floating one. That's it. Okay, that means this is floating. Okay, and this we already know, float is floating and all those things. Okay, I hope you understood this point. Now let's come to the data types of Verilog. This was the first value set of Verilog, different types of values. Now there are mainly two data types of Verilog. First is var, and then next is reg data type. So var is the default data type. By default, if you don't mention anything, like in the previous few cases you have seen, if I don't mention anything, it automatically becomes a var data type. But for reg data type, we have to explicitly tell the compiler or the Verilog compiler to that it is a reg data type. So when I write something like this, if I write input AB and output CD, input AB and output CD, basically this is var, nothing is mentioned. So Verilog will assume these to be var. They are just simply 4 wires, that's it. They are just simply 4 wires, A, B, C, D, that's it. Okay. So I hope you have understood this point. Now what is reg? Reg, right, is used only in behavioral blocks. Okay, reg is used only in behavioral blocks. Okay, now think of this as variables in C. Okay, this is not a hardware actually, just a variable, simple variable, that's it. Not a hardware. This is not a hardware register, something like that. Just a simply it is a variable. It is just a variable. Okay, so I hope you understood this value. So here if I write a statement like this, always A and B, okay, this should be at the rate, not and, sorry, A comma B, then it is I can write like something like this, m equals to x and not x and b, A and B, just something like this. So if I write something like this, that means that, can you define me what this code does, part of code does? Basically it is telling me when A and B changes, then like m will be A and B. If A and B doesn't change, it will simply hold. Okay, if A or B change, like, or I can do what I can do, this, right, this I can write as some C and D. Okay, like you will understand this better now. So now if A or B changes, anything, A or not and A or B, any of this changes, then m value will be C and D. If A or B doesn't change, then m will not change its value, it will store it, hold its previous value. That is the like that is what a registered data type does. Okay, so I will write here, if A or B changes, then m will be equals to C and D, and if it doesn't change, otherwise m will hold the previous values. Okay, so that is one thing, that is the advantage of like this reg data type. So holds previous value like this, right, is different from like C doesn't have any time implemented inside it, right? This has time. So previously means 1 second previously or 2 seconds previously, whatever it was holding, it will hold the same value. So I hope now you have understood the differences between the wire data type. Wire is simply just a wire. It's just simply wire. There is no delay. Whatever I will pull it up, pull down, it will pull up or pull down. Okay, that's it. These wires are used to interconnect between different modules and blocks. Okay, so that's what wires are used. Okay, so like in always block sometimes we need to hold the value, right? In always block we need to hold the value. That's why we use anything that is on the left hand side of inside the always block, right, will be a rich data type. So I will write here as we need to hold values uh, in, so anything inside always block, anything on the left hand side LHS of always block should have rich data type. And if you remember, in data flow statements we are using assign, and with assign we are using wires, not rich, because assign means just connect that wire, just connect that wire. That is what we mean by assign. Okay, so few key points that I should say is that your rich, right, let me name this reg y. Okay, let me name output reg x. Okay, and let me name input reg ab. Okay, now out of this, right, few are invalid. So this is valid because this is a intermediate signal. A intermediate signal can be a reg data type, intermediate signal. Okay, it may be required to store the value. Output can be registers because sometimes output has to hold the value. After that it will send it to the next module, right? So output can be a register, it is fine, but input can never be register. Why input can never be a reg data type, not register, sorry, of reg data type? Why? Because input needs to drive the module, right? We're providing some input, we're driving it, right? Drive the module. So if I am providing it some input, if I am driving the module, that means basically input can never be rich. Okay, output can be rich, but input can never be rich. Input has to be always wire. So this is a very, very important information that you should know. Okay, this can cause syntax errors, okay, in your code or program. Okay, so that was about the inputs and outputs. Now sorry, like I'm recording this at like very night and like very sleepy right now. So now we will discuss about the number representation in Verilog. Okay, so Verilog provides two types of number representation. One is size, another one is unsized. So sized meaning the size of the number, right, is fixed. I will explain you what is size. Size of number is fixed. Unsized means unsized. I will not fix the size of the number. Size of the number will be predefined by the compiler. Generally, the Verilog compiler set like we have a default value that is 32 bits. The size of the number will be 32 bits. Bits mean 32 bits. Like each number, right, each length is 1 bit, 0 or 1. It can be 0 or 1 in binary, right? So like this, I will have 32 bits. Okay, that is the meaning of bits. Additionally, Verilog, like for simulation purpose, it supports the unknown and high impedance values. Also, it supports negative numbers, underscores, For readability, I will explain what is underscore and the question mark symbol for don't care conditions. We'll understand this, where x and z are undesired values as explained previously. So let us understand the sized numbers now. So the sized numbers is this one. Okay, so here like this is the format of like writing a size number. So in a size number, the format is something like this. First I will define the size, then the base format. Base format meaning whether it will be written in binary, octal or not. So I hope you have studied number systems, you know basic number systems, right? So whether I have written in binary, octal or not, then the number itself. Okay, so this, right, first I will write size, then I will put a tick or like in commas, inverted commas, single inverted comma, tick, like this. Okay, so I will show you a few examples. This is one of the example. So this 4 is the size of the number. It is a 4-bit number. This 4 is 4-bit number. Then I am doing a tick. Then I am writing B. B means binary. Okay. Then I am writing 4 ones because it is a 4-bit number. I can only write 4 ones. If you write more than this, right, what it will do? If you write 5 ones, it will truncate the MSB. That is this one. Simply truncate the MSB. It will ignore the MSB. Okay, it will only take 4 bits. That's it. I'll show you example as well, don't worry. And in hex, if you want to write, so 12 means 12 bits, and each each character in hex, right, is 4 bits. I hope you have studied number systems, you know this very well. HABE, okay, this is a 12-bit hexadecimal number. Then this is 16, this is a 16-bit number, D255. This is in the decimal scale. Okay, so this is how we write the numbers, base and all those things. If I have an unsized number, I will basically not define the size. By default, it will be a 32-bit number. Okay, 32-bit number. So if it is a 32-bit number, you might have a question. So if I write something like this, 101, it is a 32-bit number, right? But I'm only writing this much. So what happens to the other 29 bits? So other 29 bits basically are what? Zeros on the MSB. So if I add zeros on the MSB, nothing will change, right? So exactly that is what Verilog also does. It adds zeros on the left hand side of the number. Okay, so pretty simple, not that difficult. Just for defining this, right, by default it is decimal. If no base is mentioned, by default it is a decimal number. That is also very, very important point to note, is by default it will be a decimal number. Let me choose some other color. Okay, this is also a very, very poor color. Can I choose anything that is okay? Nothing is good, man. Nothing goes good in any. Will this go good? No, nothing is going good. I don't know why. So just I will mark this important, right? Decimal by default. Okay, so these are few things that I wanted to explain. So as I was explaining, let's say I have this number. This is a 7-bit number. I have defined it to be 7-bit number, but I am writing hex FE. You know, each character in hex, right, has 4 bits. So total I am giving the input as 4 bits. So what will happen? So let me first write the number. So this is 1111, and this will be what? FE. So this will be 1110. Now basically what will happen? I will combine the numbers from the left hand side. I will start 4 bits completed, 5, 6, 7. I will stop here. I will ignore this bit. Okay, so ultimately my number will be 111110. This will be my number. Let me name this variable as any variable you want to name, x. Okay, x will be equals to this. So basically this one, right, will be truncated. It will not take the MSB. Okay, so basically what we do, truncate the higher order bits. Okay, if I had, let's say, given here 6, then it would have truncated these 2 bits. If I had here 5, then it would have truncated the 3 bits from the MSB. Okay, so this is one of the things. Now let's discuss about unknown. Again, as explained previously, unknown and unknown is not synthesizable. As I have explained, unknown is not synthesizable. High impedance is synthesizable. Okay, so represents unknown value. This represents floating state. Pretty simple. So here, right, 1 3. So the first 8 bits of this hex number is defined, but the last 4 LSB bits, right, x, is not defined. So basically this x in binary, it is understood like this: x x x x. Okay, last 4 bits will be undefined, first 8 bits are defined. Okay, so if I write x or z, it basically does, it sets the 4 bits. In octal, if I write x or z, it sets the 3 bits. In binary, it will set only 1 bit. I hope you know what octal. In octal, if I write x, it is like each digit is 3 bit. In hex, each digit is 4 bit. I hope you know all these things. A negative number, it is represented in 2's complement. I hope you know 2's complement as well. This I have taught multiple times in COA, and in our digital course as well. We have learned what is 2's complement, and format is negative sign. So let's understand with this example, right? If I have this 3 here, now if I want to basically write this in 2's complement, first the MSB will be sign bit. If it is a 6-bit number, MSB will be sign bit. So 1 is fixed here. Okay, I have 5 bits remaining to define this 3. So 3, positive 3 is defined as, in 5-bit number, it is defined as 00011. Okay, now I will convert it into 2's complement. 2's complement of this will be, first I will take the complement of this, that will be 11100, then I will add 1 with it, so that will be 11101. Okay, so this is the 2's complement. So in the computer, in the Verilog, what is stored? The number stored is 11101. This is stored. The first one is sign bit, and all the other bits are in the 2's complement fashion. Now if I want to come back, how the Verilog will compile it back? So Verilog will basically do this. Okay, Verilog, it will first check the sign bit. Sign bit is 1, that means it is a negative number. Then it will take the 2's complement, like of the other remaining bits. So first it will do the complement of the remaining bits. So it is 00010, then it will add 1, so it will be 00011. So ultimately this is what, 3, so minus 3. So that's how I get back to minus 3. That's how it is stored in 2's complement format. But this is a legal way to store a number, but this is illegal. Illegal meaning this is not valid. Okay, so for tick d minus 2, I cannot store minus 2 here. No, minus sign has to be before the this size of the number, right? Then only it understands. Minus 2 here is illegal. Verilog will throw an error. I will show you in the code as well. Okay, don't worry about it. So like here only I have an example as well. This is a 6-bit number. Okay, just notice that I have given it a 5-bit input, because one of the bit is sign bit, that will be taken care, right? One of the bit will be sign bit. So now if I again write it in 2's complement, what will Verilog understand? Verilog obviously doesn't understand negative numbers. It will store it in 2's complement format. So 2's complement format will be basically this, that first it is minus sign, so the first bit will be 1, then the other bits I will complement. This will be 00100, then I will add, it will be 00101. Okay, so it will be 00101. Okay, so next is this 00101. So this is what the Verilog will store, computer will store. Now if I want to come back, I will repeat the process. Okay, I will show you in code, don't worry about it. I'll show everything in code. Okay, so here, right, numbers, sometimes what happens, if I want to define a 16-bit number, right, and like it is very huge, 16-bit number is very huge. So what we do, we have a underscore sign. So what does the underscore sign does? Underscore sign basically tells me that Verilog ignores it. Verilog will simply ignore it. Okay, it is just there for readability purpose, used for readability purpose. So we read it, that's it, that is the only purpose. Except Verilog will ignore it, just for our sake, for better readability of the code. We have this, you can place it here as well, after this 1, you can place it here after this 0. It is there just for readability purpose, nothing else. Okay, Verilog just ignores it. Okay, but one thing, it cannot be the first character of the number. Here after B, right, I cannot choose it, I cannot choose it here. Okay, that is just prohibited. So I hope you understood. So this, right, because like it becomes messier, that's why we have an underscore to for better readability. Okay, so here like alternative to, like question mark also can be used, question mark or can also like all be used. So alternative to x, not z, sorry, this will be x, this will not be z. Alternative to x, question mark also sometimes can be used. Okay, So again, it enhances readability for case X and case Z statement. I will explain what is case X and case Z later on. Don't worry about that right now. Okay. So if I say a code here, okay, and this is what I have defined in Verilog. Okay. For now, skip this. What is this? Skip this. Don't have to understand. Just think it as of a variable. Okay. So A is storing this value. So if I have not defined anything, right, this will be by default, this will be 32-bit number. This will be 32-bit number. Okay. Is it really? So to understand this better, right, I will go to the code and explain this thing better. Okay. So you will not understand it here perfectly. So let's go to the code basically. So if I go to the code, so first thing what you have to know is that ultimately I have actually changed my code. So previously I was using address example, but now I am actually using some other file. Okay, size number, something like that. Okay, let me just cross it because I already open it again. So if I reopen it again, just hold on, give me a second. This will be size number test and size number test bench. Okay, so the two files are open. So now as I have changed my file location, so again I have to cd to that file location. So I will do cd and this is my file location. Again you have to do the same only. This is a separate file, so you have to cd to this file location, and these two right, you can ignore. That you don't have to worry about this right now. This is just for the test bench purpose, just for getting the output. Okay, that is what is this for. You can ignore this. Just simply copy and paste this in on your Verilog file. And this is the module size number check, which is here, size number check, and this is the module name, module under test. Okay, we are just simply printing the statements. So here, right, for now, if you don't understand what is this, I will just explain it to you. If you don't, it's totally fine. We'll understand this in very detailed manner later on. Okay, so ultimately this ABC are all 64-bit numbers whose LSB is 0, LSB bit is 0th bit, and MSB bit is 63rd bit. Okay, these are all 64-bit number. So now next what I am doing is simply I am storing the lowest 32 bits of A as this, which doesn't have any size mentioned, right? So by default it will choose 32 bits. Okay, so if it is 32 bits, can you tell me that how many bits I have written over here? So the number of bits written over here is this is in hex, so this will be 4, 4, 4 and 4. So 16 bits I have told it. So what about the other 16 bits? It will assume it to be 0 because this itself is a 32 bit. So the MSBs will be filled with 0 as explained in the just 10 minutes before starting of this, before this coding example, right? Now what about this one? Again I am defining a 8-bit number. This is again a hex, and this is a 8-bit number, E and F. So it will just fill up the 8 bits. Okay, what will happen to the other bits? Because here, right, I am only storing the 32 bits. What about the other 32 bits? Because overall this is a 64-bit number. Let's see for C, right, I am only storing 16 bits. Again this is the hex number. You can do binary, anything. Again you can do underscore. I will show you underscore as well. It will not matter. Okay, so here if I see here, this C is this, right? Now what will be the output? What will happen to the other 48 bits? 16 bit is stored. What will happen to the other 48 bits? Those will be all what? Those will be all unknown, okay, or undefined. That is X. If I now try to print the output of this, right, because like it is already shown. So I will do cd this, then I will do iVerilog. I will have the name VBP file, and I will have the test bench which I am running, right? This is the test bench. I'm just simulating on the test bench. Okay. So if I do enter, then if I none of the error statement has happened, that means it has compiled perfectly. Then if I do VBP, I am seeing that yes, the first 32 bits is totally correct, but the other 32 bits, right, are all filled with X. Other 32 bits are all filled with X. That means what? That means they are uninitialized. So this will only be at simulation. If you actually do synthesize, there will be some value 1 or 0, right? If you actually measure with a multimeter, but in simulation they will be X because they are uninitialized. That means you have messed up. What have I messed up? I have only initialized the 32 bits, but I have not initialized the other 32 bits of A. Same for C. If you see C, right, sorry not C, for B. If you see B, again I'm initializing the 32 bits. So automatically, even if I feed it a 8-bit number, automatically it understands that the other 32 it will just initialize with 0. Okay, it will automatically understand that. Now if I change this, right, if I change this to 7, basically the 8-bit number, so now again if I compile this and again if I see the output of this, you will see now only E and F are there and all the other are X. Basically I gave it a 8-bit input, hence others are X. It was not the case in the previous case. It was storing zeros up until the last 32 bits. Okay, this is for B. For C, I am storing a 16-bit number 45. Okay, 45. So for C, right, it simply gives it 45. Why? Because I have not defined, like, don't worry, I will come to this later on. I have not defined what bits need to store. So it assumes that I am storing all the bits, that is 64 bits in C. So that's why it directly stores 45 and all the other bits, right, are 0, 0, 0. So as they are 0, so it only displays 45. Okay. So now one thing I want to show you, that we did some example, right? I did this example. I will show you in my tab. We did this example, correct? The negative number. So I will show you the negative number. Quickly I will show you the negative number. So now if I write the same thing in C, right? If I, or let me define another variable. Let me define another variable like reg. This is a 6-bit number. So it will be 5:0 then D. Okay, and this D has the value. This D has the value as this -6. Okay, okay, I'm not showing you the code, sorry. So the code will be here. So I'm doing this. So D has the value -6. Okay, -6. Where did I go? Yeah. Okay, the mouse pointer is not here. Yeah, it has the value -6 tick B 11011. Okay, so in Verilog actually what it stores, that I want to display. So I will display this, like don't worry, I will talk about this display statement in very much detail. I'm just ignoring this for now. Just look at the output. That is the important point. Just look at the output. Okay, so this will be comma D. Okay, so now again if I compile this, okay, something has happened. Okay, I have forgotten to put a semicolon. So don't forget to put the semicolon. That is very important. Okay, so now if I do this, now if I see, right, what does your D store? D stores 100101. Is that what we derived? If I come back to my tablet, okay, what is D storing? D is storing 10001. Okay, so let me just do one thing. One thing I want to do, power tools, I just want to show you one thing. If I can somehow magnify something, that is what I'm trying to figure out here. Just give me a second. Okay, this is not there. Okay, that is not there. Magnification is not there. Okay, fine. So like as I was explaining, that you see that this is what we derive, right? 10101. Isn't that what we are seeing in the Verilog code? Isn't that the same output? 10101. That is the same thing, right? That means whatever we have learned is correct only. Okay, so this was one short thing that I wanted to explain about the negative numbers. Now let's come to the other concept that I was explaining, that X extension and Z extension. Before that, I want to show you that if I put an underscore here, there will not be any difference to my output. Okay, I will get the same output. If I again recompile it, okay, it will not throw any error, it will not give any other output, same output it will give. Okay, but if I have a underscore here, then it will throw a output. Okay, it will throw a output, it throws a output. If I have an underscore here, it again throws output. So I cannot have an underscore in the starting, right? I can have underscore after the starting. That's it. That is one more thing I wanted to show. So that is about the first part. Let's come to the next part. Okay, next part is this one. Now what we are doing, right, this X, what this X does is basically it tells the this, right, it is a 32-bit number, so it tells that fill the 4 bits, okay, 4 bits, the highest 4 bits of the 32-bit number as X. Okay, same thing here only. It tells the fill the what do you say, fill the bits from 11 to 8 as Z, high impedance, that is Z extension. Basically it is a hex number, so it will fill the 4 bits as Z. If it was octal, it would have filled 3 z's. Okay, so what is zero extension? Zero extension, it pads 15 zeros. So if I like zero extension is very simple. If I have just written here 1, but this is a hex number, so what will happen? I have just provided 1 bit, right? Or like if I write this in binary, so this is in binary. So I have just provided this is a 16-bit number, but I have only provided a single bit, that is 1. All the other bits will be padded with 15 zeros. All the MSBs will be padded with 15 zeros. So let us check the output of this one. So if I check the output of this one, here you can see, right, all the rest of the bits are padded with 0 for the C. For the B, if I check, ABC1 is filled, and the what I will do, right, this right, best thing what you can do, we can store all the 64 bits, then you will be able to understand this in a better manner. Okay, just hold on, just ignore all these for now. I will explain this later on. Just focus on the outputs. Okay, so now if I compile this, okay, still it is the same thing only. Okay, it basically extends x. Okay, if I have this x somewhere around here, what difference will it make? Yeah, so basically, right, if I have this x at the front, what it will do is it will extend x throughout the whole size of the number. Okay, I haven't not saved it, I think. Yeah, this will extend the x throughout the whole number. Okay, if I have the x at the start or the z at the start, but if I somehow move the x after telling it a digit, then what will happen is that basically I will just turn my camera properly. Yeah, basically what it will do is it will just fill the 4 bits of x after a. So if I just run this, compile this code again, here you can see just the 4 bits, right, are filled with x. Okay, if you want to print this in binary, you can print this in binary. So how do you print in binary? You just write here %b. All those things I will explain later on, don't worry. So if I print it in binary, right, you see the 4 bits have been filled with x. The first bit is a, that is 1010. The last 4 digits, like other bits are all okay. Again, if this starts with z, then all the bits are filled with z. If I move this z here, okay, and if I print this in binary, then what will happen is that again, if you see 4 bits have been filled with z, that is the purpose of z. Okay, so question mark I will come to later on. It is just an alternative for don't care, don't worry about that for now. So this was about the size numbers. Okay, so now let's come to the assign statements. Okay, so what is the assign keyword? The assign keyword in Verilog is used for continuous assignments to drive values onto net data type. Okay, what is net data type? I will come to that. Basically, wire data type. Okay, net has wire data type, which we have already learned. Okay, so a continuous assignment is evaluated, updated whenever the right hand side expression changes. It is a key mechanism for modeling combinational logic. Basically, what does assign means? Assign means if I have a wire here a, and if I have a wire b, if I write assign a equals to b, that basically means I make an interconnection of a and b. So obviously it's just a wire interconnection. If b changes, a also will change. That is what assignment means. Assignment is only used for continuous variables. Continuous meaning signal is continuous, right? It is a continuous variable. It is not a discrete variable. It is driving continuously 1, it is driving continuously 0. Okay, so that is what it means. So like assignment, the must have net data type. The right hand side and the left hand side must be of net data type. Net data type meaning wire. I will explain net data type bit more later on. Okay, on the left hand side. So registers, res data type, and variables like integers, real cannot be used on the LHS. So I will explain what are these later on, but these cannot be used on the left hand side of a assign statement. These cannot be used. Okay, the right hand side can be a constant, it can be a signal or an expression involving signal. Like it can be a wire as well, it can be a number, real number, anything it can be. Okay, right hand side can be anything. Okay, but it can be register as well. Right hand side can be registered as well. The assign statement updates whenever signal in the RHS changes. This we already know. If it is interconnected with a wire, this will change automatically. This will change. Okay, so the right hand side can be a net and reg data type. Net and reg data type. Okay, continuous logic. It is like combination logic. It is used for describing combination logic like address and multiplexer. Like whenever you are using Dataflow level of modeling, you have seen we are always using assign statements. Okay, so it is mainly used in data flow level of modeling. Okay, so this right assign, then there is drive strength, then there is delay, then list of assignments. So what is drive strength? Drive strength means how much strength it has. I will explain this drive strength later on. We'll come to this, don't worry about this. Okay, for now just understand this. We have a wire ABC, assign C, A and B. Basically what it does is it first does the AND. Basically A and B will go to a AND gate. Okay, then the output, I have a C wire here, this is AB, the output will be interconnected from the AND gate. That is what this statement basically means in hardware. Okay, example 2, assign data out 4101. So I am assigning a constant value. So this right, actually this is a four wire system. Okay, 4 wires I have, it's a 4-bit number, that's why it's a 4 wire. So in single shot, if I want to write, right, I can write this in single shot like this and write 4. That means it has 4 wires in short notation. Okay, so this right is constant, like this value will be constant 1010. Okay, something like this, and this will be my total wire, data out wire. Okay, again whenever this, like here, right, whenever A and B will be updated, C will be automatically updated. So if A and B are updated, your C automatically gets updated. Okay, C automatically gets updated. Okay, this one here again, right, doing the same thing only. We are ORing it, then ANDing it, then assigning it to the value. Okay, same things only. Here again the same thing only. We're adding two values, then assigning the value. We can do, these are all legal. These are all legal. Okay, again here also we're assigning constant value, we're assigning complement, we're assigning x and y. Okay, all these things are legal. Okay, now what is this delay? I will come to this drive strength in the next lecture. I will not discuss about this drive strength today. But what is this delay? Delay is, what the name suggests, is delay. But remember, delays are not synthesizable. That is, for simulation it is fine, but for synthesizability, right, we cannot do it. Delays are not synthesizable. Okay, so basically what I mean by delay, basically if I write this statement, assign hash 10 out equals to in1 into. So what will happen? It will calculate the in1 and into. In1 and into will be computed. Okay, but it will not directly be reflected here. Okay, it will be reflected after a delay of 10 nanoseconds. So there is a delay of 10 nanoseconds. Okay, after that only this output will be updated. So sometimes for simulation purpose we have to add in a delay for simulation. Okay, this is used for simulation, not for synthesis. Okay, so this is basically what assign keyword does. Now if you are illegally using it, how you can illegally using it? So this is one of the illegal use, right? So where we have a reg data type and I am doing, these are all reg, so I am assigning C to A and B. Right hand side is fine, but left hand side cannot be reg. This cannot be a reg. Okay, this has to be a what do you say, net data type or wire data type. Okay, so now let's come to the code. I will show you the code real quick. So this code is in different file. Let me open that file. So assign keyword. So if I open the assign test bench and the code. Okay, yeah. So let me close the previous one. So now again, as I have opened a new file and the location of this file is different, right? So again I have to cd to that file. So I will do cd and this location will be different. So it will be basics of Verilog. Then it will not be getting familiar. It will not be size numbers. It will be okay. This is wrong. These are all wrong. This is, yeah, next example. Okay, so okay. Best way is you go to your location and just copy the location. Assign keyword. You go to a location and just copy this location. That would be the best thing. Do remember to insert this in colons, right? Within colons. So let me paste this. Yeah, now it is done. So I have cd this. Now again I have to recompile this. Before recompiling this, I will show you the code. So this is the code. these are okay, these are string, this we will come to later on, not I think not for today's lecture. Let's check the assign statement. So this is the assign statement, right? So this is just a model, simple model, and we want to check whether everything is happening correctly or not. Okay, so we want to run this test bench and we want to get the output of this test bench. Okay, this can be inside here as well. Okay, this can be here as well. Initial, don't worry about this initial begin thing. Okay, don't have to worry about this. I will explain this later on. This will come later on. Okay, don't worry about this initial begin at all. So now this is the test bench. I just want to check the output, right? So first is this is not allowed. Okay, so this is currently commented out, so this will be fine for now. So I am defining it output B. So nothing is mentioned, that means it is of where data type, and on the left hand side of a assign statement where can be there. Okay, but this is not valid, right? This is not valid. So first of all I will comment this one out. For now I will just see the output of this. So I have made few changes to the code because there were few errors. So like I have made it 10-bit because obviously I am storing 10-bit number, this has to be 10-bit, right? This is just a where. So now if I run the code, okay, I have to run the code. So if I run the code, first of all you have to cd to the current directory because I have changed my file, so I have to cd to the current directory. So I am doing that. I hope you are also doing the same thing. So then you have to compile the code. I will log assign, the names have changed, it is assign keyword test. Okay, so then you compile the code, then again you press VVP to see the output. Now you can see safely I can get the output as 234, which I have assigned here. Okay, no problems about that. Now let's say I want to assign a, like this is a 1-bit register and I want to assign 0 to it. Will I be able to do it? If I try to do it, right, if I try to run the program again, okay, it says reg A cannot be driven by a primitive or continuous assignment. So basically it throws up error. We cannot do it. We cannot assign a register a continuous wire or something. We cannot connect it. Okay, this is not valid, this is illegal. Again, if I do something like this, assign C equals to A, this is also not valid because A is a register, right? So if I remove this, okay, I will not remove this, I will write somewhere. So this, right, if I remove the assign statement, just write initial. Don't worry about initial and begin, don't worry, I will explain this later on. You can ignore this for now. Okay, initial, begin and end. So now if I want to do, right, like A has value 0, that is totally legal, but what about the C value? So let's see if it will crib or it will not crib. Okay, so again it is telling that reg C cannot be driven by primitives or continuous assignment. Now if I write here this as B, okay, this as B, now will it be able to store it? Is it valid? Yes, it does not throw any error, right? Now if I check the output, yeah, B is 0 as stored here. If I store here B as 1, it will give me output as 1. Okay, so I hope you have understood the difference between the assign operator. Okay, B as 1. Okay, I'm getting B as 1. So like this is about the assign operator. Now let's come back to our like notes. Okay, so I hope you understood this thing. So we have understood about the assign operators and all those things. Now few more things, few basic things I will explain. I will go through them a bit fast because they are not that important. First thing is, like, tokens are the smallest building block of a language. Basically they are syntax. It is basically syntax, right? Syntax. So this is just for readability purpose, reading purpose. So first one is the keyword. Keyword is basically like this module. Module is a keyword. They are reserved words that have predefined meanings in Verilog, like module, end module, input, output, always, assign. They are all keywords, right? You cannot use assign as a name or something. Okay, don't use that. Then there is identifiers, names given to variables, modules or instances, that is given by you, but they have few rules. You cannot choose any name, right? The rules is they must start with a letter or underscore followed by letters, digits or underscores. Okay, so this is a valid name. Okay, clock signal, but you cannot start one clock signal. Okay, you cannot do it, it will throw an error. Okay, so I will just show you quickly in the code. I will show you this one. Okay, so if I go back to the code and just quickly show you, let me write this reg A name as underscore A. If I write underscore A, there will not be any error. Okay, if I recompile it, there will not, okay, there will still be error. Okay, So yeah, this is not possible. Underscore, oh sorry, this underscore a, also I have to write underscore a here as well. Okay, sorry, if I change this underscore a, where I have to change underscore a. So now if I do I Verilog, yeah, it will not throw any error. It is totally fine, right? But let's say I change my variable name which starts with a number. Okay, which starts with a number. If it starts with a number, let's say 1a, I write a variable name like this 1a. Okay, will it throw any error or it will not throw any error? Let's see. So again it throws error, syntax error, invalid modular time. Okay, so this cannot start with a number. We cannot start with a number. So make sure that your whatever identifier you're choosing, it should not start with a number. If you are choosing a number, right, then you are doing something wrong. Okay, so let me turn this off. So yeah, I hope you have understood this thing, what kind of valid legal identifiers you can choose. Next is operators. So we will discuss about operators later on, don't worry. For now just understand these are used to perform operation on data. Plus is addition, subtraction, multiplication, division. Division is not synthesizable, which I will explain later on. Then this is AND operation, OR operation, equals to, not equals to. Don't worry, we'll understand this later on. Literals, these are fixed value assigned to variables like 1b1, 4101, these are all literals. Okay, these are fixed values. This is a constant, or you can say these are all constant that can be assigned to variables. Okay. Next is punctuations or separators, like this semicolon, right? Semicolon is there. Semicolon is always used to explain the end of a statement, end of a line, same as C. Okay, so these are all there. Parenthesis, this is also will be used. Then comments are this double slash, basically we use to explain for better readability, explain to the user who is seeing the code what this code does. This is not functional. Okay, this is not of the part of the code, this is just for readability purpose. Just like here, I will show you comments. Okay, this, right, not this one. Like if this is commented, right, that means this will not be executed. Even if I have a compiler error, like let me name this assignment as 1 assign b, the compiler will ignore this line, it will not take care, it will not throw any error. Okay, even though my variable name is something weird, it will not throw any error. Okay, yeah, I'm showing you the code only. Okay, it will not throw any error. So I hope you understood this point. It is just comments for better readability. Like in the previous lectures as well, I had few comments like this one, right? It will throw out error, something like that. So this is just for better code readability. That's it. Okay. So yeah, let me come back to the tablet again. So yeah, so this is the for the comments. Then we have numbers. Numbers I've already explained what are numbers, and yeah, these are just examples of whatever tokens we have and what we use. Okay, so comments I've explained what are comments, just for better readability purpose. So strings are also there. Strings, you can go through this like multi-line comments, how can I write single line comments, all these things are like pretty boring. You can read this, they are just documentations. Identifiers are there, like how what are legal, these are all illegal identifiers, these are legal identifiers, as I have explained. And dollar sign, you can never use dollar sign at the start, right? Dollar sign are reserved for system tasks like display finish. I will explain what is display finish later on, you don't have to worry about it. Okay, so none of the identifiers can start with a dollar sign. Okay, so these are all examples of valid identifiers, and these are all legal identifiers. Okay, and these are all illegal identifiers. We cannot start with dollar, we cannot start with reserved keywords. Okay, we cannot just use an identifier whose name is always is reserved. Okay, so yeah, this was about it. Escape characters, these are all backslash, this is not that important, these are also used for reserved words. This I will come to later on, you can skip this for now. Escape characters are used here. These are used for like print statements or something. Okay, containing special characters. So this declares where with escape identifier a plus b plus c. So if I use this escape always, right, then what I can do is, right, I can use this even if it's illegal, I can use this. Okay, that is what this escape characters does. It helps us escaping. In Verilog, escape characters allows you to use special characters, reserve words or any unconventional naming in your identifier. Let's say if you want to, sir मेरे को use करना है, always use करना है मेरे को identifier में, करना ही है, तो what you do, you start with the escape character. If you name a variable like this, where slash forward slash a always, even though always is a keyword, but it will ignore because it understands that it is a identifier. We can use this as an identifier name. Like if I print this, right, display always slash always, what it will print, it will print just always equals to 0. So although the variable name is illegal, always is reserved keyword, but still I am able to use it with the help of escape character. Okay, that is the main use case. Like this, right, is what is this identifier 1 2 3 4, but if I use escape character I will be able to use this. Okay, that is the use case of escape identifiers. Okay, or characters, whichever one you want to say. Okay, so yeah, that's basically it. These are few more escape characters. These are used in display statement. I will come to this later on, don't have to worry about this right now. Okay, so one more small thing is left. I will come to the code about the strings and all. Strings obviously these are not synthesizable, you cannot synthesize, but for readability purpose strings will be there, right? Just like C program, a string in Verilog is sequence of just hold on, a string is a like just hold on, I will just check if all the codes and all those things are fine or not. Okay, yeah. So before going that, I think I missed few points. What point I missed? I missed this point, that here, right, I had a few keywords. This keywords I had to mention about the keywords. Where is the keyword? Yeah, I had to mention about this, that all the keywords, right, will be lowercase. Okay, this is very important because Verilog is case sensitive. Just remember this, all keywords, if I was forgetting this, will be case sensitive. Okay, so this is one sorry, not case sensitive, sorry, lowercase. None of the keywords will be uppercase. If you observe, display, monitor, all those statements are all lower cases. Okay, so now let's let me explain, like this identifiers already I have explained. These things are already explained. Okay, these are very simple. Okay, again here, right, this is illegal. Like I forgot to mention this, this is illegal. Why is this illegal? Because reg is a keyword, I cannot use it as a identifier. You can only use it if you use a backslash, like forward slash, like this, forward slash reg, yes, then you can use forward slash reg equals to 1b1, you can use it, no problems. But you cannot use this one. Okay, reg value you can use. Value is not a keyword, value is not a keyword. This is a identifier, that is a name of the variable, and this is a keyword. Okay, I hope you understood the difference between keyword and identifier. Okay, so like these are basic things only. So now let's understand about strings. Strings in Verilog is a sequence of characters enclosed within double quotes. Okay, whatever I write, like this is a string, but of course your computer doesn't understand characters, right? It understands zeros and ones. So of course for each character we have a code, and that code is known as ASCII code. So it is mapped to a code. Let's say this, right, is mapped to 0, like 220 code, is S is mapped to 230 code. Okay, I'm just giving you an example, these are not the exact codes. So that is what is written over here, that each characters are mapped to a 1 byte ASCII values. Okay, so strings must fit a single line, it cannot have line breaks, we cannot have multi-line strings, that is not allowed. ASCII representation, each characters in a string correspond to its ASCII values. Strings are stored as array of 8-bit values. We'll understand with a coding example. Strings are often used for debugging, basically for display and monitor statements, nothing else, right? It is not obviously not synthesizable. How can you synthesize strings? You cannot synthesize strings, right? Not synthesizable. Okay, important point. So these are few examples, like few examples of valid strings and invalid string. Of course I will go to the code and there I will like explain these things. Okay, so first example is this one. This register is there, this is a string, like register has like these values, like this is a size of the register, it is starting from 160 to 1. So it has up to, like each character, right, is 8 bits, correct? Each character is 8 bits. So that's why I needed a string of 20 characters. So each character has 8 bits, so 8 into 20 total size I need to have on this string, else it will not be able to store the string, right? So if I store str equals to hello Verilog, so even though this is 1 2 3 4 5 6 7 8 9 10 11 12, but the others it will just store 0. Okay, it will not store it. Of course it has to store the space as well. Space is also a like character. Okay, so I will go to the code. There I will display all this. So let me just quickly go into the code. Okay, let me quickly go into the code. So if I go into the code, so now I will show you the string example. So now, right, the test bench for the assigned keyword, I will just comment it out because I don't want to understand assigned keyword for now. I want to understand the string. Okay, so uncomment the string module. So this is a module for a correct string. So like this is just for displaying purpose. So I'm storing this variable string hello Verilog. Okay, so now if I compile this code and run this code, you can see the output is the string is hello Verilog. You can write anything, right? Hello Verilog, I am Anish. But you have to be careful that you are within the limits. If you are outside the limits, few things will be few things will be truncated. So still you can see that Verilog I am Anish. Okay, it is collected, but the other, right, hello and the space, it automatically is not visible. What is happening? Basically, if you like see how many characters I have, 1 2 3 4 5 6 7 8. Okay, let me just 1 2 3 4 5 6. Now this is 7, this is 8 9 10, then 12, then this is 5, right? So this is 17 and 18. 18 is there and I have space here. So it basically there is a space also. So it only has up to 20 characters. Now if I increase the size of this, right, let me make it up to 30 characters, something like that. Now it will not truncate. It will not truncate it out. If I see, yes, now it is printing it correctly. Okay, so just be careful about that. Just be careful about this. You have to choose a size perfectly. So that's why we generally don't use variables as for storing strings, because strings are generally not used in code as per se. Just in the display statements strings are used, and there we know we don't need to store it anywhere, right? We directly write the string. Okay, that is the advantage. So just be careful regarding this thing. Okay, now let me show you the example for an invalid string. Okay, so if I show you the example of an invalid string, so this is a module for an invalid string. Okay, so now I will call a invalid string. This was the string example. Now I want to call the module invalid string. Okay, module under test. Okay, so now again if I run this code, like what is wrong with this code? So here, right, I am trying to span in multiple lines on this string. That is not allowed. In Verilog it is not allowed actually. In C it might be allowed, in Verilog it is not allowed. So now if I run this code, yeah, it is telling me that missing closing code for the string in line 32. If I move on to the line 32 is here. It has to have a closing code, right? It doesn't like totally span the line. So there is some error. So we cannot initialize our strings like this, right? We cannot do this. So if I do this now, if I do this, if I don't have the only a single line, then if I again compile, it will compile no problems. But if I have an enter here, if I press enter, if I span multiple lines, again if I try to compile, it will throw out an error. So just be careful regarding this invalid string. Okay, that is what I wanted to show. Basically it is used for debugging purpose, just like this, right? Display the string is for this kind of cases. So basic C, you know, so that is what we use. So I will just comment this one out, and this one will be again commented. Okay, so that is for the code. Let me go back and just explain few more things. Okay, so string is done. So you can do few string manipulations. Verilog does not have a built-in function for string manipulation like concatenation or substring. In C, if you know this, great. If you don't know this, skip this. This must be done manually using array or bit slicing. So what does array or bit slicing mean? This I will come to later on as well. Just wanted to show you a bit of glimpse about array and bit slicing. So again, if I uncomment this module, okay, and now if I uncomment the string example. Now let's say if I don't want to display the whole string, I just want to display the first 20 characters. Okay, so if I want to display the first 20 characters, I will display it like this. Okay, 20:1. Now it will display the first 20 characters, where 1 is the LSB and 20 is the MSB. Okay, so now if I do I Verilog and if I see the output, it only displays this. Okay, only displays H. Okay, why is it displaying only H? Okay, it should be 8 into this, right? Sorry, I messed up. So because each character is of 8 bits, so I have to multiply 8 with it. Okay, so now if I recompile it, now if you see, yeah, Verilog I'm Anish. Okay, so it is only showing the first 20 characters. Now if I want to just see the first 10 characters, like this you can see the first 10 characters. This is the I am Manish, okay, just the first 10 characters. Like this you can slice, do the array slicing. If you know C, then you understand what is array slicing. If you don't know this, ignore this, we'll come back to this later on. Don't worry about this for now, okay. So this is how you can manipulate the strings as well, okay. So let me come back to our notes. So yeah, that is done. String we can compare our strings with their respective ASCII values. It will not be used, so I'm ignoring it. I'm not explaining it. Few escape characters are there, special characters like /n. /n is used for like entering a line, new line, okay. /t is for tab, double quotes is for double quotes basically. So what it means, I will just come back to the code again. So there is, like, if I just uncomment this again, okay, if I just uncomment this again, so there is no way for me to print double quote, right? I cannot print a double quote here, okay. It will throw out error, like this code will throw out error. So what we do is, to print a double quote, we first write the backslash, then I print a double quote. So then, right, it will not throw out error, okay. Just I will show you an example. If I directly try to print a double quote, it will throw out error. So if I try to compile, yeah, it throws the error. Now instead of this double quote, right, if I have a backslash, it will not throw out error. It will not print the backslash, it will just print the double quote. Now you might have a doubt, see, it is printing in the double quote. You might have a doubt, sir, how do I print a backslash? So you write twice the backslash. Now whatever is after this backslash, right, it will print, okay. So that we will come to that backslash as well, escape characters as well. I will explain you later as well. So now if I try to print this, it will print the backslash. You see, okay, I have not saved it. You have to save it, then you have to recompile. So if I recompile, you see I'm getting a backslash. Same as if I write n here, right, it will just after this, right, it will insert a next line. It will, like this, all these things will go to the next line. So if I again recompile, if you see, yeah, I am Manish is in the next line. Now if I have a T basically means a tab space, right? It just inserts a tab of space. So if I write T, basically what will happen, yeah, there will be a tab of space. If I remove this T, there won't be any tab space. Okay, you see, there isn't any space here, there was space, okay. So these are few characters. You can play around with this, like these are not that super important for me to explain. These are just for you to play around, okay. So white spaces, you have understand, like /b is for blank space, /t is for tab, /n is for new line, and white spaces is used to separate tokens but is otherwise ignored. Just like here, right, if you see white spaces in the print statement, if I have a space, it will reflect here. But generally if I write something like this, right, this b space equals to space a, this space is ignored by the compiler while it is compiling a like statement, but inside the double quotes it will just print that space. That's it. That is just what I wanted to tell to you guys, okay. So it is not, white space is not ignored in strings, it is ignored in the Verilog, in the code itself, okay. So like I went a bit fast in the last few slides because these are not that important. This you can play around, the notes are there, just see the notes and try to play around. This is not for me to explain, this is for you to explore, okay. So that's it for this lecture, and in the next lecture we'll continue basically of whatever we have learned, okay. So next lecture we'll learn about signal strengths. I told you a thing about strength, we'll learn about signal strengths, and we'll learn about nets, okay. I've told you basic things about net, that net is wire. We'll understand much deeper what is nets, okay. So that's it for this video. If you enjoyed this video, make sure to hit the like button and comment below how are you feeling regarding this Verilog series. Thank you for watching, and I hope to see you in the next lecture. Until then, happy learning.